So in the last video we got up to a point on number 13 in section 3.4 where we had this equation for that represented the second derivative. Alright? So we can look at this and say, alright, well it's very similar in structure to what we had for the function definition itself, which was x squared plus 1 over x squared minus 1. The numerator is always positive in the original function, and then we gave some reasoning about that the sign always had to remain either positive or negative because since the numerator was always positive, this function was never actually equal to 0. So wherever the function was defined, it was either equal to something that was positive in a particular interval and negative in a particular interval. Those intervals were determined by whenever the denominator was 0, we had some vertical asymptotes, and that kind of partitioned out the real line into the intervals outside of and between those vertical asymptotes. So again here, 4 times 3x squared plus 1. Our numerator of 4 times 3x squared plus 1, our numerator is never actually equal to 0. Because if I had a negative number, I would square it and multiply it by 3. Since I squared it, it would become positive. I would multiply it by 3 and add 1. I get out a positive number. If I put in 0, I get out 0 times 3, which is 0 plus 1, I get out 1. If it's some negative number, when I square the negative number, it becomes positive, multiplied by 3 and 1 again, still positive. So our numerator is never equal to 0. We have some vertical asymptotes where the denominator is equal to 0 at x equal to negative 1 and x equal to positive 1. Other than that, between these vertical asymptotes and outside of those vertical asymptotes, which is from negative infinity to negative 1, from negative 1 to 1, and from 1 to positive infinity, we have a continuous function. So that means that we could use some little test points here, right? So here we have from negative infinity to negative 1. We'll use a test point of x equal to negative 2, which is in this open interval. So our denominator, is what determines what the actual sign of the function will be. So of our second derivative. So at x equal to negative 2, if I take negative 2 and throw it into x plus 1, I get negative 2 plus 1, which is negative, right? And then negative 2 minus 1, also negative. So here I have positive. That means that my function of my second derivative is going to be greater than 0 from negative infinity to negative 1, or negative 1 all the way out for all numbers which are less than negative 1. So since our second derivative is always greater than 0 on that interval, then my function is concave up. And that agrees with what we were looking at intuitively before, just at the graph of the function. And for the other two, if I use a test point of 0, if I throw 0 into here, I get 0 plus 1, 1 cubed, positive, 0 minus 1, negative, so I have negative times a positive, which is negative. So our second derivative is going to be less than 0 between negative 1 and 1. For my interval from 1 to positive infinity, if I use a test point of 2, throw 2 into x plus 1, that becomes 3. 3 is going to be positive. If I throw 2 into x minus 1, that is also going to be positive, so that will be positive. So I have concave up, concave down, and then concave up again. And if I look at my graph that I had looked at before, that order for each one of those intervals is exactly what we had determined. So, and we know that that is true, not just in a graphical sense, but we worked through the algebra and confirmed it using the theorems in our arsenal. So that was the second part of number 13 for section 3.4.